One of the common uses of exponential functions is working with money, compound interest. And it's calculated by the formula A of t equals P. Now, P is our principal. Again, that's still our starting amount. So when we're dealing with money, that could be a deposit or an investment, multiplied by 100% of your principal, plus the next one is a fraction. It's going to be R over N. R is our rate, but it needs to be in decimal form. They may use the phrase APR as annual percentage rate or nominal rate. And the N is the number of times compounded per year. Now, down below it says the term compounding refers to the interest it's earned not only on the original value, but on the interest itself. For example, if it's compounded monthly, like a savings account, that means whatever money you deposited in that first month will get interest that first month. The second month, you'll earn interest again, not only on your first deposit, but also on that interest that you earned the first month. So it's interest upon interest. We love compounding. But that's why we take the R divided by the N. If you get a 5% interest rate, you do not get the entire full 5% every month. That is an annual percentage rate. So they're going to divide that interest rate by however many times it's compounded throughout the year. So it's your rate divided by N. And then you want to know how many times is it actually being compounded. Our exponent is going to be N times T, where T is years, so the number of years that you are investing something. So if it's 3 years, but it's compounded monthly, then you're going to have a total of 38 months the interest is being given. So that's why it's N times T. Oh, and the A of T is your amount after 2 years. So hopefully that formula makes a little bit of sense to you. Let's take a look at example 3. At birth, Maria's parents set aside $8,000 in an account designed to help to pay for her college education. That would be your initial amount. Okay, you deposited $8,000. How much will Maria's account be worth? So that's asking us to find the account balance at the end by her 18th birthday. Now that sounds a little bit tricky, but they gave it to her at birth, 18 birthdays. That means 18 years later. And they said the interest rate was 8.4%. By the way, if you find something that gives you 8.4%, share the love. Most savings account right now is like 0.3, maybe 0.03. So this is our rate, but remember our rate is always a decimal form. So don't forget to move that decimal 2 places. So we would get 0.084. That is probably the biggest careless error that I see in pre-calculus. And then it's compounded monthly. So that means our N is 12. It's compounded every month in the year. So let's remember our formula, where the account balance equals our initial amount times 100% of the original, plus our interest rate divided by the number of times compounded to the power of the number of compounds times the number of years. So let's fill in what we know, plug and chug. We're solving for A. Our principal is 8,000. We have 1 plus 0.084 divided by 12 to the power of 12 times 18. I recommend you put all of this in your calculator at once. Otherwise, carry out all of your decimals and be very careful about your order of operations. Let's take a look at what that would look like in our calculators. So if we were to plug in 8,000 times 1 plus 0.084 divided by 12, close parenthesis, to the power of, now for some of you, it's just going to show a hat. Others, it will actually bring it up to the exponent. So I would put the entire exponent in parentheses. We have 12, the number of times compounded, times 18, close parenthesis. That way, your calculator knows that it's that entire product that is your exponent, not just the 12. Because remember, it does order of operation. So if we hit enter, then we get a more accurate amount to the tens, hundreds place, because we're dealing with change. We're dealing with money. So our account balance on her 18th birthday is approximately $36,095.71. For the next question, it says, suppose Maria will need $50,000 to help her pay for her college education. This means we want that to be our account balance at the time she turns 18, so in 18 years. So how much money should her parents invest? Okay, so we're looking for the principal amount this time, our initial value. If the account earns 5.75% interest, so 0.0575, compounded quarterly. Quarter, remember there's 4 quarters in a dollar. Quarterly means by 4, so 4 times a year. Tip from your Aunt Lainey, whenever you're working with a new formula, rewrite the generic formula every time you use it, and that helps you to remember it. So this time they gave us the 50,000 as our A value. We're trying to solve for P. We have 1 plus our interest rate of 0.0575 divided by our number of compounds, which is 4, to the exponent of 4 times 18. So if we're solving for P, once again, we don't want to put things in our calculator and have to round more than once. So we're going to divide everything that's being multiplied by P. So we'll get 50,000 divided by 1 plus 0.0575 divided by 4 to the power of 72. That's the 4 times 18. So if we're going to put all of that in our calculator at once, we would have 50,000 divided by, in parentheses, 1 plus 0.0575 divided by 4, close parentheses, to the power of, and I went ahead and multiplied the 4 and 18, so that gave us a 72. So if we hit enter, we get $17,892, and it rounds to 68 cents. That means her parents need to invest $17,892.68 at the time that she's born in order for her to have $50,000 at that interest rate by the time she turns 18. This comes in very handy if you're trying to save up for a car or the down payment of a house. It's nice to have. Now, when do we use E? When we have a continuous growth or decay. And that's represented by the formula where we have A times E to the RT, where A again is the initial amount, and that initial amount is typically greater than 0. R is the continuous growth rate if R is a positive number, or the continuous decay rate if R is a negative number. Okay. So when we talk about continuous growth or decay, think of it in terms of like a compost, or if you're trying to carbon date material that you found in an archaeological dig, it is constantly decomposing. Unlike compound interest, you only get interest every month or every 3 months or every year. But some things just continually grow, like plants, right? They're continually growing, your hair, your fingernails. So whenever we're dealing with a continuous growth or decay, we generally use this formula. We can convert it from a continuous to an annual, but it depends on how they're giving us the information as to which formula we're using. And again, T is the time elapsed. Now, for business applications or money, when we have continuously compounded interest, they just use P instead of A. It's the exact same thing. So you may have heard of the PERT formula. P is still your principal or initial amount. R is the interest rate, generally per year. And T is the time or period of investment, how long you're leaving the money in the bank. So suppose we've invested $10,000 in an account, okay? So that $10,000 investment is our starting amount. So that's our P, our principal. And the account is earning 2.1% interest. So that's our rate, but we would write it in decimal form. And the interest is compounded continuously. This tells us to use E. In other words, the PE to the RT. Then it asks, how many years will it take? So they're wanting to know the time for our investment to reach $15,000. So that is our account balance, or the future balance of this account. So when we consider our formula where the account balance equals the principal times E to the rate times time, let's fill in what we're given and solve for what we're looking for. So we want the account to be worth $15,000. Our principal or starting amount is $10,000 times E. Remember, E is a number, not a variable. Taken to the rate of 0.021. The rate is positive because we are earning. In other words, the account hopefully will be increasing, right? It's growing. And we want to know the time T. So we need to solve for our unknown T. Well, notice T is in the exponent position. So that's kind of our hint that we're going to use logarithms to solve this. But we need to get the base of that exponent alone first. So we're going to divide both sides by the $10,000. That was our principal. That leaves us with 1.5 equals E to the 0.021t. And again, what we have in our toolbox to get that variable out of the exponent position is going to be logarithms. But since our base is E, we are going to take the natural log of both sides, because remember, the understood base of a natural log is E. So the left-hand side just gives us the natural log of 1.5. The right-hand side, since the base of our logarithm and the base of our argument are the same, it leaves us just the exponent of 0.021t. And so to get the t by itself, we divide both sides by the 0.021, and that will give us a t value of approximately 19.3 years. So it will take approximately 19.3 years for the account to grow to $15,000. All right, so that is it. See you again soon. Bye.